Can you hear me now?
Yeah, we can hear you.
Okay, sorry about that. Sometimes the microphone just went crazy. I just used my microphone and it didn't work afterwards. That is strange. Okay, so what am I saying is I think some of you guys have started working on the question 1 of assignment 2, and I have found a problem. Well, actually, an issue with the code that is in the given example. So I think last time I said you can feel free to reuse this code in your solution if you want to compute the digest of the SHA-256 hash function. And the problem is, if you use this code, you probably will have some not readable or not recognizable digest that is being computed. So the problem happens on the last line of this function, which is basically just we are constructing a string object, and we are passing in the string object with the computed hash, and then with the length of the hash, and try to convert it into a string, a printable string or readable string. But the problem is, if you do that, you will probably end up with something that looks like this, like those garbage values. Like here, the student is trying to reuse the same function and follow the same procedure that is posted on the handout, but the computed hash looks like this. So the problem is, because I didn't check this code by myself, because this code was provided by the instructor or by the professor, and after I look up the documentation of the OpenSSL library, it turns out this computed hash is returned as binary form. So that means if you're just printing out the binary result of this hash, because it's not ASCII encoded or Unicode encoded, that means anything will be treated as anything this binary will be treated as a character, and because we don't have that kind of weird encoding, that's why we have this garbage value over here. So in order to solve this, there is a Stack Overflow answer that I found. So I'm just gonna copy and paste this link to the chat, so feel free to use this answer. So you see, from this answer, this guy is basically doing the same thing. We have a unsigned character array to store the results, and we have the context. We have initialized it, we have updated, we have finalized it. But instead of just casting the binary hash directly as a string object, this guy is using a string stream to try to convert it into a hexadecimal human readable format, and then return this hexadecimal string as a string. And this is the correct way to do this. And I have tested this method out. It works. It worked well for me. So I hopefully this will also work for you. And yeah, that's one thing I have to mention before anything gets started. Does that make sense? And do you guys have further questions regarding to an assignment? So feel free to reuse this code. It's okay. This is not part of this is not the core part of this this question. So it's okay to copy and paste the string stream. Do I need to slide this code? You can, but you don't have to. I know. I mean, if I see the exact same code that has been repeated, I know you guys are using this. Are taking this answer in your solution. It's okay. And also for this question, I don't think for this question 1, I don't think you have to submit your code, because what we really want is you want to brute force the MAC address, and we don't really care how you implement it, as long as you can brute force it the correct result. It should be okay. Make sense? Okay. So yeah, that's one thing I have to mention before we get started. I think you guys have the idea of how this question should be solved, and the questions actually on the protest, everyone gets a different question. So you have a different question set. That means you cannot simply just copy and paste other solution, because you guys are doing different MAC addresses, and also you guys are being provided with different hash values. So it's all right to reuse this code. You don't have to cite it as well, because you don't have to submit it anyways. All right, so that's all I need to say about this question, also about assignment 2. So just go back to what we have to discuss for the week, which is the passwords and kerbals. So there are 2 topics on this handout, this homework handout. The first topic is about password resets. So consider this article here, which is posted by the IT department of UCalgary. And I think most of you guys know that after a year, if you haven't changed your password of the UCalgary account for a year, then you will receive an email saying that, oh, you haven't changed your password for a year, please change it now, please reset your password. And I think that's annoying, and most of us also think that's annoying as well. And this is their reason. Why should I change my password on a regular basis? Answer is, password management is about mitigating or decreasing the risk. There's no such thing as a secure password. By changing your password in regular intervals, you are decreasing the likelihood of someone guessing your password and accessing your login ID. So the question is this statement true? Like, does changing your password from X to Y decrease the chance of it being guessed? Or what are the conditions under this is true, and when might this claim not hold? Might not hold? Any ideas? You can feel free to unmute yourself or just type into the chat. It's not true. Password is not wrong. Okay, so what is your like further explanation? And when does this might be hold? Like, what are the assumptions? Y has to be a better password than X. Yeah, that's a reasonable answer, but what do you mean by a better password? So think about this. I have a password that hasn't changed for a year. And there are 2 cases that might affect the security of my password. That is, either I have reused this password from other website, or the database that is storing this password has been compromised, like the UCalgary password database has been compromised. Those are the 2 cases that might affect the security of my password, like directly. If this 2 case doesn't hold, that means the attacker who wants to get access to my account, there's only one way for them. That is just by guessing out, by brute forcing my password, right? So, so that brings up another problem, which is if both of those cases is not true, like the university's database is not compromised and I'm not reusing the password that I've been used for other websites, and it's still considered as a secure password, right? But you're asking me to change it because you think it is safer to change it to something else. But think about how most authentication system is implemented. Like, you're supposed to have a username and you have your password, and the username is probably anyone can guess it as long as they know your full name, right? And now the problem is the password. And on the most authentication systems, the password has a minimum length and a maximum length, right? Like, for example, like 8 bytes or 8 characters at minimum, and let's say 32 characters at maximum. And the available characters are also limited. You can only use alphabet characters, uppercase and lowercase, and numerical numbers, and probably some special characters, right? So the whole password set is finite. So when I'm saying the whole password is finite, that means you can literally list all the available or all the possible passwords within this set. And if you are changing this password, if you are changing your password on a regular basis, this will bring up an issue that is, the more changes you make, the more likely you're going to use, the more likely the attacker will find a match one, right? So that's why this statement is not true, especially there's no compromise of the database and there's no reuse from the other website. And also there is another issue that about resetting your password or resetting your or changing your password on a regular basis. The other issue is humans are making their password easy to remember. Well, if you are changing your password from a random string to another random string, and there's no connection in between them, and also there's no connection in between the new password to yourself, like your birthday, your name, or your father's name, your pet's name, and your favorite band, your favorite music. Those are the possible things you can easily memorize, and you probably want to use those as your password because they're easy to remember. So that actually limits the available password for you. So you cannot just grab a random number like this one. I don't think anyone would use this 106462E413422B204. They use this as their password because it's not reasonable to remember such a random string, right? So that will also limit the passwords, the available password domain or the available password space you can think of. So that means if someone who knows you very well, he knows who you are, he knows what's your birthday, he knows where you live, he knows the street number, he knows everything about you. He can just literally just use those information to minimize the unsuccessful brute force trials, because he knows you definitely not gonna use this random string as your password because you cannot remember it, right? So actually, the usable name, the usable passwords for each like individual of us is very limited, and changing from one to another increase the chance of another of the attacker increase the success rate of attacker that can successfully guess out your password. So this is definitely not a good suggestion when considering password reset. Like, there's no such a thing as a secure password. Well, there is no such a thing as a secure password, but there is a such thing that there is a safer password, right? It is not leaked. It is not being reused, and I'm not using all the information about myself to create this password. And now you're asking me to change it to something that I might be more familiar, like it's easier for me to memorize, but it's actually not safer. So that is why this is not true. But when might this claim might hold? Can anyone give me an example? Like, what are the assumptions this statement might be true if that assumption is true? Like, what's the reason we want to change a password? Just think about that, and what are the assumptions that drive us into a password reset, and also makes the reset, like makes the password safer by doing the reset. Like, what are the assumptions? If I told someone my password, yeah, that's exactly true. If you told someone your password, and then you have more people knowing the password, and that guy maybe tell your password to another guy, and this is endless, right? So that might be true if you want to reset your password. And also, if the database is being compromised and the database storing your password is in plain text or other things, like the unsafe hash function, the unsafe ways to store the password in the database in a data breach, or you have reused the password for uCalgary, and that the other website you use the same password has a their database has been compromised, and that is the case when you need to consider reset your password. Just imagine, just take a very simple example. Has your bank ever told you, well, you have been used your password for 10 years, now it's good to change them, or it's good to reset them? No, never, right? And think about why they don't implement such policy on changing your password for your bank account, and that might be the reason why this statement is not a very good. It is not a very good suggestion overall. Okay, so that is all we need to talk about for the password resets. And for the next topic, which is the rainbow tables. And I think the description about this rainbow table is way too abstract and is very hard for me to demonstrate what are the ideas behind those. So instead of using those questions, I have created a PowerPoint or slides that gives you a better understanding of how rainbow table works and how you can use them. And I also have the same questions, like same type of questions, but it's just with an example. So just a refresh over here. Why do we need this? Well, imagine you're the attacker, and most of the authentication system, they have their password stored in a hash form. Now you have the hash. Your next goal is to get the plain text or get the real password from those hash values. The easiest way to do this is to pre-compute each one of them. And this is the most straightforward one, because you're just guessing a bunch of possible passwords and storing them into a database. And next time, if someone has used the same password, they have the same hash, right? So you can just look up that hash. And I know, well, this guy are using, let's say, the the QWERTY as their password because they have the same hash. So this is the easiest way to do this. But the problem about this method is you are going to store a lot of password and hash chain or hash pair in this database, and this database will be very, very large. And that is for some people that is probably larger than their hard drive, and it's just doesn't make any sense. If we extend the maximum password length to, let's say, 64 characters, then that will be even more. So this is a very straightforward idea and also easy to implement method, but it just takes so much space to do it. Because of that, we came up with an idea about a hash chain. So the hash chain basically just, I have my initial guess, which is the password, and then I compute the hash of it, like the next hexadecimal representation of the hash, and then I define a reduce function, or the professor called it the reverse function. But what does the reverse function, or what does this reduce function do? It just maps the hexadecimal space back to a plain text. You can imagine this reduce function as another form of hash function, but the hash function maps the plain text to hexadecimal space, but our reduce function does the other way. So you have to know that this reduce function is not the reverse of the hash, because you see, I'm reversing, or I'm reducing this hexadecimal from this to a plain text VFKKD. But if I compute the real hash of this VFKKD, this is the actual hash of this plain text. So don't take this as your digest guess for this specific plain text. Is just another type of hash function, but that doesn't hold some cryptographic properties like the rollback resistance or the prediction resistance. It just doesn't have those resistance, but it still can be considered as a hash function. Even we call it a reduce function or reverse function. Confused how you get VFKKD? Well, this depends on what type of reduce function you're using. Like I can define a type of reduce function that just takes all the numbers. Oh, sorry, that is not a number. Well, that takes all the numbers in a hexadecimal string. So I will define my own R as taking all the numbers from a hexadecimal string. So if I apply my reduce function on this input, then the output of my reduce function would be 4, 6, 8. And then I will just replace this as 4, 6, 8. Or I can just define it as I'm going to take all the characters out. So that's another reduce function I can come up with. So I can do it FDD. This is just an example. Like the VFKKD is just followed some rule, and I can get this VFKKD. And this is exactly what the hash function does. The hash function also follows some rule to convert a input into a output. So that's why I'm saying that this reverse function or this reduce function is just another type of hash function. And we just keep doing the same thing. So we have our initial guess, we hash it, we reduce it, and we have another plain text, and then we hash it, we reduce it until we have reached the end. And this is how, this is the beauty of the hash chain, the interesting part about this hash chain. We are not storing all the intermediate values. we only store these two, the password and the crypto, because with the head of the chain, or with the tail of the chain, we can easily compute all the intermediate values on the fly, because I have my initial value. Then how do I get this one? I just use my password, hash it, and reduce it. Then I will get this one, right? So it's kind of easy to reconstruct the whole chain just by knowing the head and the tail of this chain. And this also means we can save a lot of space by not saving the intermediate values, because what we are really storing is we're storing the head and the tail, and any intermediate values can be computed on the fly. This is a very typical space-time trade-off. So we are trading some space with the time, or we are trading some time with the space. So in this case, we are reducing the amount of space we need to use compared to the very basic, like, dictionary form. We're reducing the amount of space we use. Instead, we need to take a little bit more execution time to compute the rest of them. And this is the whole idea about this hash chain. And now we know what a hash chain is and how to compute the hash chain. The problem now, suppose we have a hash value. Let's say I got this hash value from a compromised database, and I want to know what is the password corresponding to this. How do I do this? Well, because I know this is a hash value, so the first thing is I'm going to apply my reduce function on it. Why? Because I said this is a hash function, and it has a very important property that is called what we call one-way property. So it's very easy to compute from this side. I think there's something wrong with my mouse. Sorry about that. So it's very easy to compute from this side to this side, but very hard to do the opposite. And also, the reduce function is another type of hash function that is very easy to compute from this side to the other side, but very hard to compute the other way. Just take the example like this. I am defining my R function as taking all the numerical numbers from a hash string. So I know I have 486, but is this enough for me to guess what is what was the full hexadecimal string it was, right? It is very hard. There are many different combinations can have this 486, and it's also not unique. There are many possible ways to do this. So that's why I keep emphasizing an idea to you, that is, this R function or this reduce function is just another type of hash function. And that is why every time we have something to guess, we can only follow the chain. We cannot do the opposite. Like, we cannot start from this side and compute all the way to the front, or all the way to the head. It is just impossible to do so. So now we know why we want to reduce it. So the first thing is, well, I have a hash value, and the first thing I do is I'm just going to reduce it. So what is the result of the reduce function? So if I take this, if I know this exactly what is the rule about this reduce function, so the result would be crippa, right? And because I know this is the result of my reduce function, the next thing I'm going to do is I want to identify which chain properly contains my hash value. And how do we do that? Because we only store the head and the tail of it, that means we can only compare this with the head and the tail. So in this case, I know crippa is at the tail of this chain. So that means it is very likely that our hash value is on the chain. And that is exactly what this chain for, right? So after I can identify there is a very high chance that my hash value is on this chain, I can just reconstruct the whole chain. Like I know it's my hash value will be on this chain, and how do I determine the plain text of it? I just reconstruct the chain from the beginning. That's why I have my head stored in the hash table or in the hash chain. So I just start from the password, hash it, and to get the hash, is this hash, does this hash match to my hash? No, it doesn't, right? So that is a miss. So we just do the same thing. I reduce my hash and compute the hash. Is this hash what am I looking for? It is, right? They're the same hash. So what is the plain text that was used to generate this hash? It is the VFKKD. So now I know the plain text of this hash value is VFKKD. Make sense? Or any questions regarding to the process? Okay, so that's one possible scenario. What about it's not a direct result? Like take an example of this one. I have this hash value for a 46FD8D. So just like what I did for the previous one, the first thing is I'm going to reduce it. So what's the result? It's VFKKD. Is VFKKD, does this one matches any head or tail? Well, just assume I only have this one chain in my database. It doesn't, right? Because if we compare this with the tail, it's not. If we compare this with the head, it's not. So what do? We just repeat this process. We take the hash of this result of this reduce function, and then we reduce it again. So what is the hash of VFKKD? That is this hash value over there. And then if I reduce it, then I will get triplet. So because I have the triplet, and now I am comparing this triplet with all the head and the tails I have in my database, and I know I have a chain that ends with triplet. So that actually tells me it is very likely this hash value is on this chain. So we just do the same thing. So we just start with the head, we hash it, and we get our hash value. Is this hash value I'm looking for? Yes, it is. That means this is the password I'm looking for. And that is another case about when the first match doesn't hit, but the second match or third or even more matches hit. And what about we have a hash that doesn't exist in all the known chains? Like just always assume this is the only chain I have in my database. And what if we have a hash that doesn't exist? Let's say I'm just gonna write some random values like 0, 1, A, B, C, D, E, F. This is the hash value I have, and it's not on the chain, right? So what I do? I first reduce it, and will probably output. It probably will give me an output like A, B, C, D, E. So it's A, B, C, D, E on the tail or on the head? It's not, right? So we just hash it and reduce it. And this will probably give me C, D, E, F, G. And we check again. If any tail or head has this thing. No, it doesn't. So now I have a question for you. When should I stop doing this recursive reduce and hash operation? I can continue doing this like forever, but what is the point that I know this hash doesn't exist in all known chains? Like how do I know I don't have this thing in all the known chains? Can someone tells me how to do that? Because I can literally just keep doing this forever. Like keep doing the reverse, keep doing the hash, and taking the whole thing into the next iteration, and keep doing the reduce, the hash, take the whole thing. I can keep doing this forever. If we get to the original hash, not really. Do it no more times than the length of the longest chain in the base. Yeah, that is correct. Because we know for all the chains, we have how do we produce those chains? We're basically just hashing it, reducing it. And if we take this two operations as one iteration, that means the longest chain in my database only takes 2 iterations. So that means if after 2 iterations of this RH, I cannot find any head or tail that matches my known chains in the database, I know it is not in the database. So, any questions regarding to this? Make sense? I have to make sure everyone knows exactly what this hashing is doing, because you will be tested just on the test. If you don't know anything, please explain again. Explain which part? No more times than. Oh, so just think about how do we generate those chains, because we have our initial guess, right? We have our initial guess. This is the initial guess. And how do we reach the end of this chain? We know we have taken one iteration of hash and reduce to get this, and take a second iteration of hash and reduce to get this, and then we stop there. So that also means if I am trying to find out something, if they are on the chain, I should take no more than 2 iterations to find out if it's on the chain. Because that is the longest chain I have, right? I don't, if I want to do a third, like a third iteration, then I can keep doing it. But because the database only contains all the hash chains that with 2 iterations, so that means if after 2 iterations of this reduce and hash, if I cannot find any matches, that means there isn't a hash chain that contains our hash. Okay. So that is basically how the classic hash chain works. And it has a very serious problem. That is collusion. Because we know that both the H and R, they are hash functions. And for hash functions, it's inevitably to have collisions. And with this very classic definition of this hash chain, what would we end up with if we have a collision, like let's say here, if the collision starts here, then anything afterwards will be the same. And you may think, well, that is not a big deal. But the problem is we cannot even identify if there are collisions happening within the within our hash chain database. Why is that? Still remember we are only storing this two, right? Because we are only storing the head and the tail of each hash chain. Just by looking at this, can you tell me, like, can you tell me if you know I have a chain that starts from garbles and ends with WNAPN, and I have another chain starts with share and ends with Kripa. Can you tell me if they have a collision in between them? No. Just by looking at this four endpoints, there's no way for us to identify, wow, there's a collision happening in the middle of them, unless you have stored all those intermediate values into our database and compare them. And that totally breaks the idea of the time-space trade-off, because the idea we are storing the head and tail is to save those space to store all the intermediate values. And now I have a problem, which is the collision will waste some chains, and that is a serious problem, because this can happen like very frequently. This collision can happen very frequently, and that will still there's so many invalid chains on the in our database that has so many collisions in between them. Does this make sense? Like, why is this a serious problem for the classic hashing definition? I want to make sure everyone knows exactly everything about this, so before we can move on to the next topic. Otherwise, it's just confusing. Sounds good? Okay, so now this is a problem. How do we solve this? So the solution is, instead of using the same reduce function again and again and again, we are using different set of reducing functions or reduce functions. So all those reduce functions, they are similar, but they are slightly different to avoid same collisions. So take an example of here. So if you compare this one with the previous one, I'm still starting with garbles and share. Because I'm using different set of reduce functions or a different hash functions, if you think that, if that is easier for you to understand, then if I have a collision happens here, like I have this hash value that has been mapped to this plain text, and here I have another hash value that maps to the same plain text. Because the reduce functions we are using is different. This is for the first iteration, and this is for the second iteration. So because of that, we are actually reducing the possibility of the same collision will happening on the same time. So the idea is, as long as the collision is not happening at the same on the same iteration or at the same time, then only part of the chain will contain the repeated values or same values. Because you see, afterwards we have some values that is the same, looks like the same, but because we are using different reduce functions, anything afterwards will be different. And that's why we want to use a different set of reduce functions for to solve this collision issue. All right, so this is why we want to use this different set of reduce functions, and now we can call this a rainbow table, because only the hash chains using different reduce functions on different iterations can be called as a rainbow table. All this, like the hash and reuse the same reduce function, we can only call them hash chains. They cannot be called as a rainbow table. Now we know how a rainbow table works. Suppose we have a hash value, and this is the hash value we got from a database compromise. Now the problem is, because I don't know what is the position of this hash value on the chain. So with the very classic reduce function, I can just keep using the same reduce function again, because that is exactly how I produce this chain. But when I'm using it, when I'm taking this idea to the rainbow table, I don't exactly know which iteration caused this hash value. So now searching the result, like searching this hash value in between all the entries in our database is a different problem. We cannot just reuse the same idea, just reduce. So can someone tell me how to find this value, like how to identify which chain contains this hash value, and how to reconstruct the whole hash chain afterwards? And this is exactly the question that has been asked on the homework handout, like the first question. We still have a second question. So can someone tell me how do I identify which hash chain contains my hash value, and how to construct it from the beginning? Any ideas? Try all of them? Yeah, that sounds not bad, but how to try all of them? Well, actually, because we are running out of time, so I'm probably gonna just tell you the answer. The answer is very simple. We assume this hash value, it is the last hash value on the chain. So first thing is, I assume this is the last hash value on the chain. So I'm just gonna take the R3, which is the last iteration, and compute this hash into our third iteration reduce function. So this will probably give me some A, B, C, D, E, right? Because we don't know what that is. And I compare A, B, C, D, E with the tail and with the head and tail. Does anyone match? No, it doesn't, right? So I'm just gonna keep doing the same thing. So now I have this A, B, C, D, E. I'm taking the hash of the A, B, C, D, E and assume, now I know it is not here. This hash value is not there. Now I assume it's here. So that's why I want to use the second iteration of our reduce function to compute this. And this will probably give me another set of plain text, let's say C, D, E, F, G. So is this on the tail or the head? No, it's not, right? So now I know it's not on this position. Now I assume it's on this position. So I just reduce it using the first reduce function, compute the hash of the whole thing, and recompute this. So now what do I have? I have my R1. So I have my CDFG gets hashed and then being reduced by this one, and this will definitely give me this result, because we're basically just assuming this like at this position, this hash value will give me something forward, and I'm gonna keep trying this until it produces exactly the same chain that I have. Right? I'm just keep doing it until I have something that is a match. And this will definitely give me the WN APN for sure. And now I know, well, is WNAPN on, is this occurring on any of the head and tail? Yes, it does. So now I can identify, wow, this is my hash value is on this chain. And now I can start reconstructing the whole hash chain and get the result of this value, which is garbles. So yeah, that's basically how we identify this hash value on a chain of a rainbow table database. And I think that is all we can do for today. And if you are still unsure or unclear about this part, try to do this when you are free and understand the idea of this, like why this work. And for the next time, we will finishing the last part of this handout, which is when we have a collision. If we have a collision, how do we solve that? And yeah, that's it for the day. Sorry for the delay, and thanks for coming.